We're used to working with Cartesian coordinates because we're working on the Cartesian number plane. There is another way of representing functions, and that's using this thing called parametric coordinates. A different way of doing it. So Cartesian, what we see is a curve that's described by one equation, and then our points, two numbers, one for the x value, one for the y value. Parametrics flips it the other way. So a curve's then described by two equations, one for the x value, one for the y value, but then the point is described by one number, and that number you substitute into both of the equations and you come up with the coordinates. Now that number is known as the parameter. Let's do our standard parabola there. Y equals x squared. That would be the Cartesian equation. One way, there's more than one way of doing it, but one way of writing it in parametrics would be like that. So the x value is described by t divided by 2, the y value t squared divided by 4. There's a certain point there, negative 1, 1. Well, that would be the Cartesian coordinates. In parametrics, that would simply be the point t equals negative 2. Because if you sub negative 2 into each of these equations, the x we get negative 1, and the y we get 4 and 4, which is positive 1. So they would still represent the same point. Okay, minus a half a quarter, Cartesian, that would be t equals negative 1. The origin, 0, 0, also when t equals 0 for this one. And so on. So a half a quarter, t is positive 1, and 1, 1, t is positive 2. So how do you change from parametrics to Cartesian? So they give you the parametric equation, but you want to know what the curve is, and you're so used to seeing it in Cartesian form, so you don't recognize it. Well, how can I do it? It basically becomes a substitution question. So x equals function t, y equals, gt. They're the parametrics. Eliminate the parameter like you would in simultaneous equations and substitute in. Here is this one. X equals 2t plus 1, y is 3t minus 2. We're going to show this does describe a straight line. So I need to make t the subject of one of these. It doesn't matter which one I pick. So I went with x. So t is a half of x minus 1. Substituted into the other one. A little bit of algebra, and there's the equation of the line. And that we recognise to be a line because it's in that form of y equals mx plus b. So that is a straight line. Ooh, what about this one? X equals 2 plus cos theta, y equals 1 plus sine theta. It's a bit hard to make theta the subject of one of these. But we've got a relationship between sine theta and cos theta, you might remember. And that's this idea. Sine squared plus cos squared is always equal to 1. So I'm going to start with that by making not theta the subject, but with x I'll make cos theta the subject. And with the y I'll make sine theta the subject. And then I can substitute in, and look what we get. We recognise that now. Well, that's a circle. Centre at 2, 1, radius 1. X equals sine theta, y equals sine 2 theta. We're going to drop a table of values for each of these different degrees we'll be substituting in, and then try and work out what this curve is. Well, there's the table filled out. So for all those values of theta, and there are the x and the y values. So what does it become? Well, there's the first point, there's the next. Oh, it's looking rather strange. What on earth is this shape? Bit hard to tell. Of course, I could pick more values of t and find out it actually ends up looking like that. A very interesting curve indeed. What is its Cartesian equation? Well, let's try and work it out. Sine 2 theta is the same as 2 sine theta cos theta. These are all results we will see later on, so don't panic too much about it now. But y would equal 2 sine theta cos theta. If I draw myself up a little triangle, I can actually now substitute in for sine theta and cos theta, but get it in terms of x. Reading off that triangle, sine theta, opposite over hypotenuse, will be x on 1. Cos theta will be the square root of 1 minus x squared on 1. So there's y equals 2x, the square root of 1 minus x squared. Now, that's not actually the equation of that curve. That's the equation of the curve. Because it's actually y squared is equal to 4x squared, 1 minus x squared. How do I know that? Well, that's all to do with the curve. I know what the picture looks like now, and the domain and range is not right. If I square it, it's great because now I can get positive and negative values for values of x and things like that. Don't panic too much about that one. I don't think we'll see those sort of parametric curves, but it's just to show you where this can go to. We can get some really nice curves using parametrics rather than Cartesian. Expanding out, there's the equation. 4x to the power of 4 minus 4x squared plus y squared is equal to 0. So 5H finishes off this topic of graphs that we've been looking at.